uh, transport layer and the internal details of transport layer, we have seen how UDP works, and then we have developed a reliable data transport using finite state machine, and then afterwards we have seen two versions of pipeline protocol, the go back and selective repeat. Now let us move towards the real implementation, the most important protocol of our TCP/IP protocol suite, that is TCP, Transmission Control Protocol. So this is going to be a long topic. So we'll first of all go through the basics of TCP, and then we'll see some advanced topics in the TCP, and that will complete our transport layer as whole. Now, what is the service model of transmission control protocol? Uh, it is a connection orientation, connection abstraction. As we know that uh, in packet switch network over internet, uh, there is no connection establishment, no real circuit establishment. So circuit establishment was there in circuit switching, like in telephone network and all, where you, before transferring any data, you need to set up the path from source to destination. In packet switch, there is no connection orientation. So you take the decision when packet arrives, store and forward devices, they see the destination address, use their forwarding table. It may be a switch table, MAC table, or a routing table of a router, and then forward it to the next hop. So your packets of a single conversation may travel along different paths, and finally they reach at the destination. So the underlying internet, the network layer, is purely connectionless. So what is TCP? What is the service model of TCP? That they are trying to provide an illusion of connection over connectionless internet. That is what is the real design goal. It's a byte stream abstraction. There is no record markers or message boundaries. So application keeps on generating bytes. Transport layer or TCP keeps on packing them and then later on unpacking them. So what is happening? Byte stream is coming from application. TCP packets them, make segments, and then repacketization at the another end. Another uh, point design issue is reliable and ordered delivery. And as we have seen, for reliable and ordered delivery, we need to have timers, we need to have sequence number, acknowledgements, and if any problem is there, there is a concept of retransmission. It's a point to point with full duplex. Means once you have a connection established, then it's an end-to-end protocol, the protocol which is implemented entirely at the ends, and full duplex. Like once a connection establishment, virtual connection establishment is there, both sides can transfer data at the same time. Now, if you see the encapsulation of TCP, so the application data, which is having application header also, and then there would be a TCP header of 20 bytes if you are not using any options, and then there would be IP header. So depending upon which version of internet protocol is getting utilized, you may have IPv4 or IPv6 header. So 20 bytes of IPv4 if no options are used in IP header, and 40 bytes of IPv6. So obviously with every packet of data in a minimal sense, 40 bytes are getting extra. 40 bytes are getting extra. 20 bytes of IP header and 20, if we are using IPv4 obviously, and 20 bytes of TCP header. And then this makes a whole IP datagram, and afterwards we need to include the Ethernet header. So this is how the TCP encapsulation is getting done. If you look at the TCP header, and this is important, we have to see this carefully. You can see that in TCP header, there are various fields. So if we arrange TCP header, and this is how we actually arrange a group of 32 bits, fine. So we have 16-bit source port and 16-bit destination port. similar to our UDP. We have sequence number of 32-bit and acknowledgement number of 32-bit. This is the important thing, window size, which is known as advertised window size. We'll be seeing this in detail later on. There's a field of 4 bits, which is giving you header length, because you may use some options also. So without options, the TCP header is of 20 bytes. But if you are using options, then you need to give the header length here so as to tell the receiver that up till which point the header is. There are some reserved, currently 0 reserve field, reserve bits, which are not used nowadays. And then there are some flags. Suppose a packet is acknowledgement, then acknowledgement flag will be up. So there is CWR flag, explicit congestion flag, urgent pointer flag, ACK flag, push flag, reset flag, SYN flag, and FIN flag. So these flags are going to identify, seeing this flag, if any flag is up or down, 0 or 1. Accordingly, you can analyze that what is going to be done with this TCP packet. Then TCP checksum of 16-bit as before, and then there is an urgent pointer. So we'll be seeing this urgent pointer also later. So this is how the TCP header looks like. We move further. Now, everything which we have seen, the detail of that. So as we have seen that there is a TCP header, the initial 16-bit, and afterwards the 16-bit are source port and destination port. So source and destination port number along with the source and destination IP address is actually going to uniquely identify each connection. So as I told you that the identification in TCP is going to be done by 4 tuple, and these are the 4 tuple: source port, destination port, source IP, and destination IP. The combination of IP address and port number is generally called a socket in TCP literature, or endpoint. This term socket appeared first in RFC 0793, the initial RFC of TCP, which was ultimately adopted as the name of Berkeley Derived Programming Interface for Network Communication. And from that point onwards, people started calling them Berkeley socket, because Berkeley has with itself the initial Unix operating system, and there the derived programming interface or application program interface was created, and then they started calling it Berkeley socket. It is a pair of sockets or endpoints which makes those 4 tuples: source port, destination port, source IP, destination IP, and that is going to uniquely identify each TCP connection. So as I told you that when you have TCP and multiple clients are connecting, you have to have different sockets for each client, and each connection is going to be identified by these 2 endpoints, and not only 2 endpoints, but their binding details, that these endpoints are bound by which IP address and which port number. So 4 tuples: source port, destination port, source IP, destination IP, is going to uniquely identify each connection. Next field, as we see in the header, is the sequence number. And what is sequence number? This is every byte is going to have a sequence number. So it's not like that every packet is going to have a sequence number. So every byte which is getting created by, this is important point, you have to make note of this, that it's a byte stream protocol. Every byte is going to have a sequence number. Now identifies the byte in the stream of data from sending TCP to the receiving TCP. TCP numbers each byte with a sequence number. And you may ask me a question, then what would the sequence number of the segment? So the sequence number of the first byte of any segment is the sequence number of, or it represents the sequence number of that segment. Now, as you later on realize that this sequence number is going to be wraparound, it may start from 0 and after 2 to the power 32 minus 1. it may wrap around. As we have seen in the GBN and SR example, that suppose there are only 2-bit sequence number, so it would be 0, 1, 2, 3, and again 0, 1, 2, 3. It is wrapping around. So it's a circular sequence number address or sequence number space, which is circular, which wraps around after reaching to 0. More on it later. As we'll see later on that this field can be extended using TCP options. In nowadays networks, this sequence number field wraps around very fast. So we need to have some extension of these sequence numbers, and we'll see that in the advanced topics of TCP. Next is acknowledgement number field in the header. And this is a little bit deviation from the GBN or SR. That's what I have highlighted also. So contains the next sequence number. Now, what do I mean by this is, suppose I take a snip of this. So what it is suggesting that acknowledgement number would be the next expected sequence number. So suppose you have sent packet number 5, 6, and 7. So if 5, 6, and 7 all are received correctly, you will be sending ACK 8. And ACK 8 means everything before 8 has been received correctly. So here the acknowledgement number would be 1 plus the last sequence number which has been received correctly and in order. In other words, it can be the next sequence number which is expected. So this is therefore the sequence number of the last successfully received byte of data plus 1, which is different from GBN. Now, if this field will be considered valid only when this ACK flag is up. This field will be considered valid only when this ACK flag is up. Otherwise, this field will not be considered and it will be ignored. So it may so happen later on you will see that acknowledgement. Suppose you have some data to send from receiver to sender on the reverse side. So you are sending a data packet. It can include acknowledgement also, and then you can make this ACK flag as 1. So the acknowledgement number field will be considered. Mostly you will see later on that acknowledgements are actually getting piggybacked over the data packet. Fine. This sending an acknowledge costs nothing more than sending any other TCP segment. The 32-bit acknowledgement number field is always part of the header, as is the acknowledgement bit field. So they are part of the header. Means very seldom you need to send the acknowledgement only, and then you need to send the empty data packet. Only header part where this acknowledgement flag is set and acknowledgement number field is filled. Next is header flags. Currently, 8-bit fields are defined for the TCP header. If you talk about older implementations of TCP before 2016, only 6 were properly understood. And nowadays, that modern implementation of TCP have, you can say a basis for all these 8 flags. CWR, congestion window reduce, later we'll see. ECN echo, explicit congestion notification echo, we'll see later on. Urgent. When the urgent flag is up, it means the urgent pointer flag field is valid. So this field will be ignored if the urgent flag, URG flag, is not up. Fine. So if urgent flag is up, then urgent pointer field is valid. It is rarely used. Acknowledgement, as I told you, the acknowledgement number field is valid, always on after the connection is established. Push, the receiver should pass this data to application as soon as possible. This is push. Suppose certain piece of data you want your receiver should not wait and send to application as quickly as possible, then you push that particular segment having this flag up, which is not properly implemented, reliably implemented, or is not used. Reset. This is important sometime, usually because of some error or something. Your TCP connection may be in a loop and it's not able to move further. Then connection can be reset by using this flag. SYN and FIN, synchronized sequence number to initiate a connection, and FIN for closing the connection. So as of now, only 3 fields are important for us. Later on, we'll pick up all these flags also. And these fields are SYN, FIN, and acknowledgement. Later on, we'll discuss CWREC also and reset also in detail. But as of now, for basics of TCP, only these 3 fields are required. Next is header length field, length of header in 32-bit word. Required because the length of option, as I told you, there is TCP options also. So you require this header length field to tell the complete header size. And with a 4-bit field, TCP is limited to a 60-byte header. Without options, the size is 20 bytes. If you have 4-bit field, why 60-byte header? 2 to the power 4 means 64. Why not 64-byte header? Anybody can tell this? What is written in the slide that if you have a 4-bit field, means you can go up to from 0 byte to the 60 byte only. Why not 64 bytes? Anybody can tell this? Yes, Abhigyan.
Sir, not able to.
Tanmay, Karimullah.
No idea, sir.
Think over it. 4-bit field can, if the 4-bit field is, it have how many options? 2 to the power 4, no? And 2 to the power 4 is what?
64.
2 to the power 4 is 64.
No.
16.
16.
16. So you can have 16 numbers over there. So suppose I want to say that header length is 20 byte. How this 4-bit field is going to be utilized? Think over it. Think by yourself. Otherwise, you'll be sitting silent. Header length, if I want to express the header length, 4 bits are reserved. 4 bits are reserved for that. Using 4 bits, you have to provide the length of header. How can you do that? And it is written there in the slide that using 4 bits, you can actually define up to, you can give a number up to 60. How? Think over it. 5 minutes. Yes. चलो अच्छा 20 बाइट कैसे एक्सप्लेन करोगे? ऐसा विज्ञान मेरे को बताना ये हेडर 20 बाइट का है और 4 बिट फील्ड है मेरे पास, कैसे यूज करेंगे इस 4 बिट को? Come on guys. See the TCP header. Do you think anything peculiar here?
So option field.
Hmm? Now
So option
suppose
field.
options are not there. So our header length will be 20 bytes. Okay. So how these 4 bits are going to be utilized to, what should I write here so that receiver can know that header length is 20 bytes? See how the header is drawn here. I'm giving you a hint.
Sir 5.
Yes, yes. Now you got. Who said this?
Sir Karimullah.
Now you are reaching because we are packing the header in 32-bit words. Okay, 32 bits means every word is having 4 bytes. Okay, so if I write 5 here in 4 bits, okay, means there are 5 words of 32 bits. Now you got the point.
Yes, sir.
So how the limit can be set up to 60?
Sir maximum is 15 for 4 bits.
Maximum 15 जा सकते हैं.
15 into 4 60.
0 से 15 जा सकते हैं. 0 नहीं ले सकते, 16 नहीं ले सकते. ठीक है. कितना जा
ठीक है.
सकते हैं? 1 से लेके 15 तक. बात समझ में आया? ठीक है.
Yes, sir.
एक की जरूरत नहीं है हमको, मिनिमम 5 तो रखना ही पड़ेगा हर बार. क्योंकि 20 बाइट तो होगा ही होगा. तो 15 तक ही जा सकते हैं. तो 15 को जब 4 से मल्टीप्लाई करेंगे, क्योंकि एक वर्ड में 4 बाइट हैं, तो 60 हो जाएगा. बात समझ में आ गया सबको? अभिज्ञान?
नो सर, थोड़ा क्लियर नहीं हो गया.
देखो, सी हियर. अगर उसको सीधे सीधे अगर इंटरप्रेट करेंगे तो हम अपन 15 बाइट तक ही लिख सकते हैं ना. सो व्हाट वी आर इंटरप्रेटिंग इट, दैट if I have written say 0 0 or 0 1 1 1, what is this number?
15.
What is this number? This is not 15.
8 8.
8 or 7?
Sorry, 8 plus 4. 7.
It is 7, no? Huh? It is 7. So if I write 7 means there are 7 words. Each word is of how many bytes? 4 bytes. Okay? So means header length is 28 bytes. Got my point? So how each word is 4 bytes? Because your TCP header is packed like that. TCP header is like 0s to 31, then again 32 to 63, then So TCP header is like this. So we see word by word. Every word is having 4 bytes. Every word is having 4 bytes. So maximum by using 4-bit, we can have 1111, which is 15. Fine. It means 15 words. Each word is of how many bytes? 4 bytes. And that's why maximally TCP header can have 60 bytes using 4-bit header length. Now you got that, Abhigyan?
Yes.
Okay. Okay. Without options, as you know, the size is 20 bytes. Next is, this is most important. Now, what is happening in TCP, as I told you, that there are two controls. One is congestion control, and another is flow control. We'll be seeing TCP flow control in detail. So what is flow control? That if suppose one end is high-end processor and other end is kind of normal desktop. So the processing speed at receiver, suppose it's a normal desktop, is dual core processor. So receiver has to do some work when it receives a TCP packet. It has to, check everything and, checksum and all and find out everything is fine, and then transfer the data to the application layer, and then only the next packet can be taken care of. So receiver is processing the packets with its own speed. Sender is suppose a high-end machine which is processing with the fastest speed. Sender can, after some time, overwhelm the receiver. So there has to be a regulation. There has to be a regulator that okay, sender should not outrun the receiver. Otherwise, what will happen is another thing that on the way routers are dropping packet, there would be a situation that receiver has to drop packet because receiver may not be having more buffer space to store the incoming packet. Receiver, I mean to say the transport layer of the receiver. So for that particular purpose, there is a flow control mechanism where receiver can tune the sending rate of sender. And every time when an acknowledgement is sent, receiver will send its remaining buffer size or the remaining window that is known as receiver advertised window. It's most important thing of TCP flow control. So every time when a sender sends a data, receiver will store the data in its buffer, that's a window, and then acknowledge if everything is fine, the data will be acknowledged, and receiver at the same time will be telling the sender the remaining window size. So that is known as advertised window, which is used for TCP flow control. It's a 16-bit field limiting the maximum window size of 65,535 bytes. And thereby it may limit the TCP throughput performance. We can have a window scale option also on TCP, which we will see in detail later in advanced topics. So we have reached up to the kind of window size in the TCP header. Now next is checksum. You know about checksum. TCP header and data in some field, the pseudo header thing which we have discussed in UDP. The TCP checksum is again similar to the UDP checksum. Then the urgent pointer field. It is valid only when the URG flag bit field is set. This pointer is nothing but a positive offset. Must be so because your segment may be having many bytes. Fine. Fine. And suppose you want to tell the receiver that okay, in these 20 bytes, these initial 5 bytes or in initial 10 bytes are most urgent. So pay attention to them first. Instead of seeing the whole segment, just pay attention to the urgent bytes. So this pointer is nothing but a positive offset must be added to a sequence number field of the segment. A sequence number field of the segment means the first byte sequence number of the segment to yield the sequence number of the last byte of urgent data. So initial some data might be urgent, which need to be taken care with highest priority. And if urgent flag is set, an urgent pointer field will be considered, then that particular urgent pointer is going to be considered the offset into that whole segment. And as I told you, this is not reliably implemented or rarely used nowadays. TCP options, after the header, after the normal header, as I shown you, there are TCP option, variable number of options. There are many options which can be utilized, and as and when advancements are taking place, uh, different options are getting implemented, which can be included as an optional part of TCP header to make your protocol more powerful. Maximum segment size option, selective acknowledgement option. These are some of the options which we are going to see in our advanced topics. Window scale option, timestamp option, or protection against wraparound of sequence numbers, PAWS option. User timeout option. Nowadays we have authentication option also, and there are many more. Fine. So in socket programming, when we see socket programming, there is a special library, sock ops. Find what are the various socket options you can include when you are creating the socket. Now let's dive into the history of TCP, that how it has evolved and what is the current status. And then slowly and gradually we'll start the basic operations of TCP. So it all started in 1975 when three-way handshake, which we are going to just see, was, and as if I may tell you that SIGCOM, Special Interests Group in Communication, is the one of the most reputed conference and associated journal of computer science or computer communication. So everybody, like the person like me who is working in computer networks, has a dream of one paper to be published in this particular conference. So it's one of the most reputed conference and associated journal of this is the ACM journal. Uh, so the in this paper, the three-way handshake was first of all, you can say published in 1975, 2 years earlier to my birth date. In 1974, before this, in IEEE transaction communication, these are two contemporary journals, special interest group in communication of ACM and IEEE transaction of communication. So these are most reputed communication journals. So in 1974, before three-way handshake, Windsurf and Bob Kahn has given the idea of TCP. And after that, three-way handshake was included by Raymond Tomlinson. क्लास है मेरी क्लास चल रही है अभी. In 1982, RFC 793, as I told you, RFC is request for comment. Suppose and there is a standard RFC track. Suppose you have a new protocol or a new standard in your mind, you have to submit your request for comments to some association, that is IETF, Internet Engineering Task Force, and then in a certain format, RFC would be published, and researchers and implementers all over the world would, the name is request for comments, will be commenting on that just to make that RFC. So initially RFC would not be standardized. So after getting all the comments and all the modifications completed, that RFC is standardized, and then RFC will become standards later on, which will be open for implementation. In 1983, Berkeley Unix, BSD Unix 4.2 came, and it started implementing the TCP/IP protocol suite in its operating system. We started supporting TCP/IP. 1984, a big development in form of Nagel's algorithm uh, came into picture to reduce overhead of small packets and is able to predict the congestion collapse. So we'll see this Nagel's algorithm in detail later. In 1986, the first congestion collapse was observed on internet. In 86, I'm telling you. At that time, internet was kind of a miniature version of today's internet. And prior to that, the congestion control, that how to control the congestion on internet or the routers and network was the duty of network layer. So if you see the old textbook, the congestion control is included in the network layer. So, and I'll tell you when we discuss further our networks that whatever is implemented in the core of the internet, means on the routers, on the forwarding devices, they become ossified, or the evolution is going to be very slow, because once we install a router, our whole network will be dependent upon that. So it would be very difficult to change the router or change the internal implementation and the codes of that router. So then they decided, the whole research community decided that it would be better to take up congestion control from the core of the internet or from the network layer to the edge of the internet, that is on the end devices. And as TCP is implemented entirely at the ends, so at the end machine, at OS level of the end machine at the host, it is very easy to have evolutions, have experimentations. So after this, the whole, you can say, body of knowledge has shifted from paying attention to towards the core of the internet to the edge of the internet. So this is the whole process. And it's an interesting one. If you are interested in, as you can see the history of internet. Kahn's algorithm came for estimating the retransmission timeout or round trip time. It's a detailed topic. I'll take 2 lectures on that. Then congestion avoidance and congestion control uh, was produced or started getting implemented. That was by Von Jacobson. And actually, again, a very interesting story in this. Von Jacobson and Raj Jain both have designed similar kind of algorithms for congestion avoidance and congestion control. Raj Jain was in some another US university, Von Jacobson was another university. And these both work published simultaneously. But because Von Jacobson has published like 3 months earlier to Raj Jain, and if you see the Von Jacobson paper, he has given credit to Raj Jain's work. So BSD Tahoe TCP implementation came 4.3 BSD, name was Tahoe. Tahoe is a lake. And then BSD Reno came with fast retransmit and delayed acknowledgements. All these things we'll see, don't worry. Then TCP Vegas came, which is not implemented. Then explicit congestion notification came from Sally and Floyd in 1994. And then transaction oriented TCP, then HOE TCP, improving TCP startup in 95. I did my +2 in 95. In 1996, I started my engineering, and our institute was not having internet at that time. So TCP selective acknowledgement came by Floyd et al. In 1996. And then FACT TCP. And up till 1996, TCP was kind of matured. After 2002, 2003, when this wireless and mobile networks came into picture, again research started in TCP area. That's again a very interesting story, because Up till now, whatever TCP has been implemented and got matured was for wired networks. It was not for wireless networks. And then after 2003, 2004, the mobile, the wireless, the Wi-Fi came, and the whole process started again. That how to make our TCP compatible with the wireless scenario. So that's again a different research issue. Now you can imagine that TCP was matured in 1996, and we had our internet in my undergraduate institute in 1990. Later, late 1997, that was through VSAT. Fine, VSAT, the satellite internet connection. Uh, Very small aperture terminal used to have a chattery kind of thing, and then we used to get internet. And at that time, sending a email was like a email is typed and you compose and you press button, and then after 10 minutes or so you'll get the notification that your email has been sent, sometime more than that. So see how TCP has evolved and how far behind uh, our countries were. But if you talk about nowadays, all are at the same place. So whatever research we are doing, similar kind of researches are happening, and that is due to the you know uh, expansion of the internet. Because now we can see the other works which are happening in different universities very easily. Now, after having a little bit of uh, you know glimpse of the history, what is a TCP usage model? It's very simple. The connection setup, it's a three-way handshake. Then data transport. Sender writes data and TCP breaks data into segments or pack data into segments. And each segment will be sent over IP or the network layer. TCP is responsible for retransmitting, reordering, and removing duplicates. And then receiver reads data. After the data transfer is done, there would be a connection close or connection tear down, which is a four-step exchange. Now, how the TCP connection is set up. Now, if anybody is sleeping, please wake up because this is important. So in TCP, there would always be an active opener. Sometimes we'll say that as a client. And then there is a passive opener. Why we are saying these names? Because passive opener is ready to accept incoming connection requests, but it is not initiating any connection request. It is ready to accept. It is coolly listening for the incoming request, and that's why we say it's a passive opener. What is active opener? It explicitly sends the connection request. Okay, I want to establish a connection. So when an active opener wants to establish a connection, it will use SYN flag because it's initial thing. You are trying to synchronize with the passive opener. And it will send its own initial sequence number, which is not always 0. We'll see why. So when I say ISNC, it means client is sending its own sequence number. And if there are any options which are getting utilized, because you need to kind of negotiate the options also. And the most important option which is negotiated is MSS, maximum segment size, which is dependent upon the MTU, maximum transfer unit of the network, which is dependent upon whether it is optical fiber network or a copper network or something like that. So this is the negotiation which is getting done. That okay, I want to synchronize with you. Are you there? My initial sequence number is this. My MSS or if any other options you are using are this. I want to use these options. Are you okay with that? Now, what server will do if server is okay with that? Server will send its own segment, SYN segment that I also want to synchronize. And then it will acknowledge the SYN segment of the client. Sender will send its own sequence number, which is ISNS, initial sequence number. So two flags will be up, SYN flag from passive openers to opener to active opener, or from server to client. SYN flag will be up, ACK flag will be up. Sender will send its own sequence, initial sequence number, server. ISNS means it's a server sequence, initial sequence number. What is the acknowledgement number? Acknowledgement number would be whatever was the client initial sequence number plus 1, because now this is what is the byte I expect. This is what is the sequence number I expect. And I have acknowledged this sequence. And if any option server want to negotiate with. When client receives this, it will acknowledge the SYN packet of server. Its sequence number would be C plus 1, because that is what is the next sequence number, next byte it will send. It has already sent ISNC. The next sequence number will be ISNC plus 1. What is the acknowledgement number here? So whatever server sequence number plus 1. And then some options. This is a three-way handshake, which is going to happen before any TCP data transport. And these are the finer details which you need to include when you are setting up the TCP connection. If you have done your Wireshark labs carefully, you can see these things. You can see in your Wireshark SYN, ACK, and all those fields. So let's move ahead. The active opener initiates the thing, sends a SYN segment with SYN bit field or SYN flag up. It will specify the port number of the server to which it wants to connect, and it will send its initial sequence number. It typically sends one or more options at this point, and this is the segment number 1 from client to server. The passive opener of server responds with its own SYN segment, which contains its own initial sequence number. And it will also acknowledge the client sequence SYN packet by acknowledging with number ISNC plus 1. This is segment 2, or segment 1 from server to client. And then client must acknowledge this SYN packet of server by acknowledging it using ISNS plus 1. This is segment 3. And this is, after this everything is done, the connection is set up, and now you can transfer the data to and fro, or from one end to another end. The important thing is initial sequence number. Why we are not trying to use 0 or 1 for all the connections? The initial sequence number is actually often randomly chosen by some pseudo-random number generator or pseudo-random number function, whose range is from 0 to the power 32 minus 1. So your initial sequence number can start from anywhere. It can start from 20, it can start from 30, and then wrap around at 29. Suppose it is starting from 30, then it will wrap around again after circling at 29. The reason is why we are not using ISN not being 0 or 1 all the time. Now this is what you need to read by yourself. I'm not going to tell this answer. Why for every connection initial sequence number is randomly chosen. And from there everything will be plus 1, plus 1, plus 1. But why we are not choosing it 0 or 1? Why we are doing this one extra step? And that is what you need to study by yourself. MSS option, as I told you, is most commonly used. Each end of a connection specifies this option with the segment. What MSS option specifies? Maximum segment size, which end host is willing to receive in the reverse direction. That okay, my MSS is this, tell me your MSS, and accordingly I'll pack my segments. It will it is typically set to M2U of the directly connected network minus size of TCP and IP headers. Nowadays, everywhere the end points are usually connected to Ethernet or wired Ethernet or wireless Ethernet. So normally you will find that it is 1500 minus 40 bytes. Means 40, I'm saying if I assume that both TCP and IP headers are not using any options. So it is typically set to MSS minus size of TCP and IP headers. And this is the name of the socket option, TCP underscore max seg, which is negotiated mostly at every connection. Connection termination. Now this is a 4-step process. Active opener client can initiate the connection close. Now when active opener want to close the connection, it will send to flag fin for finishing the connection plus ACK, because whatever is the last packet it has received, it will acknowledge that with this fin packet that I have received this. It sends its own sequence number, whatever sequence number is at that point, and acknowledgement number. So whatever the last byte it wants to acknowledge, it will sending. Class ले रहा हूँ यार, कोई जरूरी काम है क्या? Requisition 15-20 मिनट बाद आना, ठीक है? Fine. So it will send fin packet with fin flag up and ACK flag up, send its own sequence number, acknowledges the last byte which it has received before, and some options. What passive opener will do? Will acknowledge this, will send its own sequence number. Acknowledgement number will be K plus 1 and some options. And if you see after this step, what is happening after this step? Connection is half closed. After this step, what client has declared that I'll not send any data. I'll send acknowledgement, but I'll not send any data. I'm ready to receive, but I'm not going to send anything. So connection is half closed. And that is needed because you might have sent, say, 5 segments, and after sending 5 segments, you might have realized that now it is time to close the connection, but those 5 segments are still in flight. Fine. You may retransmit. You may do all those kind of things, but you will not send any new data. You are declaring I want to close my connection. And when those segments which you have sent before sending the fin segment have reached there at the server might want to acknowledge them, and then you need to send the you need to receive the acknowledgement. Or at that time, server is want to send some data or its own fin segment, you need to acknowledge them. So when one end closes the connection and receives the acknowledgement, the half connection is closed. Afterwards, server will also send the fin packet with 2 flags up with its own sequence number and ACK number. Fine. So because it has not received any data, it will send the ACK number again, that whatever it has sent before. and its own sequence number. And then client will acknowledge that. So it is always half close and half open thing, and that's what is interesting here. The active closer sends a fin segment specifying the current sequence number the receiver expects to see. Fin also includes an acknowledgement for the last data sent in the other direction, that is L. The passive closer responds by acknowledging this fin packet by k plus 1, which suggests that fin is successfully received. The passive closer now becomes another active closer and send its own fin. The sequence number is equal to L. To complete the close, the final segment contains an acknowledgement for the last fin. If a fin is lost, it is retransmit until an acknowledgement for it is received. Now, why I'm sending, if you see Buckley socket, there are two system calls, close and shutdown. And what is TCP half close? What I was telling that I am done sending data. So I'm sending a fin to the other end, but I can still receive data from other until it sends me a fin. So when somebody is sending fin segment, it is not saying that I'm not ready to receive data. If any other side want to keep on sending data, I'll receive and acknowledge it until that particular other side doesn't send me a fin segment. So that's why these two are asynchronous. Both side connection close are asynchronous, and that is required actually, because both sides are moving asynchronously in time, because you keep on sending packets. So your packets might be in flight and then you send a fin segment. So you may receive acknowledgement for those packets or conversation reply for those packets. So you may both receive data and acknowledgement from the other side, and then you need to actually respond to them. You will not send any new data. Now next is flow, congestion, and error control. These are most important topics in TCP. So I'll just cover flow control today. Congestion and error control will be covered later on. Flow control are algorithms to prevent that sender should not overrun the receiver with information, as I told you. Error control are algorithms to recover from or conceal the effects from packet losses, like using retransmission. So there is no like error, only error detection is there. If there is a error detected in a packet, there would be no positive acknowledgement and it would be just like retransmission. Congestion control, it is important, as I told you, that congestion control is shifted from network layer to transport layer, or specifically to TCP. These are the algorithms to prevent that sender should not overload the network. The goal of each control mechanisms are different, but if you see the implementation closely, you'll find that the implementation of these algorithms are somewhat combined. And who is responsible and why we are saying the implementation are combined? Because every algorithm, be it flow control, error control, or congestion control, is hinged with the acknowledgement. So acknowledgement becomes a popular and an important entity in our TCP implementation. As we know, TCP receivers use acknowledgement to confirm the receipt of data to the sender. Acknowledgements can be added or piggyback to a data segment that carries data in the opposite direction. Suppose you also want to have to send some data. So with that data, you can include the acknowledgement of the previous data you have received. Acknowledgement information is included in TCP header, and these are used for all flow control, error control, and congestion control. TCP has cumulative acknowledgement, a part of GBN. An acknowledgement confirms the receipt of all unacknowledged data with a smaller sequence number. Suppose I am sending acknowledgement 40, it means it confirms the receipt of up to packet number 39. If I'm sending acknowledgement number 70, it confirms the receipt of all the packets up to byte number 69. With cumulative acknowledgement, the receiver can acknowledge only a segment if all previous segments have been received. Receiver cannot selectively acknowledge blocks of segment until unless you are using TCP SAC option, which we'll see later. So in normal classic TCP, which is not using TCP SAC option, you cannot selectively acknowledge blocks of segment which you have received correctly. The use of cumulative acknowledgements imposes constraints on the retransmission scheme. And as in GBN, in case of an error, the sender may need to retransmit all data that has not been acknowledged. So it's a bit of GBN in this sense, that if there is any problem or there is a acknowledgement loss or there is a timeout, then you need to send all the data again, because you cannot selectively, a receiver cannot selectively acknowledge block of data which it has received correctly. Flow control. TCP uses a version of sliding window flow control where sending acknowledgement is kind of separated from setting the window size at sender. Now here it is different from GBN, because in GBN we have considered a fixed window size of n. Fine. Here two things are happening. One is receiver advertised window size is also happening, which actually decides the next window size, which was taken as fixed in while explaining GBN and SR. Acknowledgements do not automatically increase the window size. You need to be dependent upon the receiver advertised window size. Acknowledgement may shift the window further in the byte stream, fine, in the sequence number, but you cannot inflate the window size or deflate. That is dependent upon the advertised window size. During connection establishment, both ends of TCP connection set the initial size of sliding window, which is 2 to the power 16 maximum sliding window size, because sliding the window size, advertised window size, is of 16 bits. Receiver returns two parameters to sender: the acknowledgement number and the advertised window size. And the interpretation at sender is like that I'm ready to receive data from starting from this acknowledgement number. Fine. Means what receiver can interpret that what sender can interpret that receiver, when receiver sends acknowledgement number and window size, that receiver is ready to receive new data starting from this acknowledgement number up to the window size, or acknowledgement number plus window size minus 1. So let's see it in detail. As in GBN, left of the left edge, before left edge sent and acknowledged, beyond right edge cannot be sent. It's an advertised window which is going to fix the size of the window, the advertised window which you are getting in the with the acknowledgement. Within the window, you know that there is a next sequence number variable where these particular segments have been sent but not acknowledged, and these can be sent before without waiting for any acknowledgement. Here, as you can see, the sender can transmit 6, 7, and 8 without waiting for any acknowledgement. See here some examples. Suppose in this situation, sender transmits byte 6. So this next sequence number field will be shifted to 7. No problem. Nothing changes, only the next sequence number bit field is shifted to 7. Now suppose acknowledgement number 5 is received with window size 4. So the next window will start from 5 and count 4 from here. 1, 2, 3, 4. It will go up to 8. So this way, using these two variables, these two values, whatever is the window size and from where the window size. So as a rule of thumb, whenever you get any problem, you just remember this thing, that left edge of the window is actually controlled by acknowledgement number. If you don't receive the acknowledgement number of the window base, window cannot be shifted. Means left edge cannot be shifted further. And right edge is controlled by the window size. So there are two variables or two values which are controlling everything. One is the acknowledgement number, which is controlling the left edge, and other is the window size, which is controlling the right edge. And from left edge to right edge, that would be the complete window. Now, in this, suppose this is the situation, and we receive acknowledgement number 5 and window size 6. Simple. You start window with 5 and you count 6. 1, 2, 3, 4, 5, 6. So this is how receiver controls whatever window or whatever buffer size or whatever space at receiver is remaining. Accordingly, receiver advertises the window and sender controls its sending rate. You can shrink the window also. Means whatever you have promised before, after advertising, you can re-advertise. No, जो promise किया था वो गलत है. Actually, this is not advisable, but as we'll see later that sometime this situation can occur that you can shrink the window, whatever you have. Now see here, example, receiver buffer is 0 to 4K initially. Sender sends 2K of data starting from sequence number 0. So right now receiver buffer is filled, 2K filled. Receiver will acknowledge byte number 2048 because it has received correctly up to 2047. And then window size is 2048, whatever remaining. Sender again send 2K data with sequence number 2048 because it has been acknowledged. And now the window is filled. Suppose receiver is not able to empty this. It has to quickly tell the sender that, okay, I am acknowledging whatever you have sent. Everything has been received correctly by acknowledgement number 4096, but my window size is 0 now. This is sometime used. Because receiver is what? Receiver is an application. Receiver is trying to send data to that application whose socket that receiver socket is getting filled by the sender. Suppose that application is not getting scheduled on the machine due to one reason or another. Might be that machine is busy running any other important processes, and your particular process, which is application of this particular connection, is not able to be scheduled and not able to process further. So then receiver has no choice but to say the sender, hey, bhai, thodi der ruk jao. I don't have any space. It is known as zero window advertisement or ZWA. It's a very interesting concept in TCP. So how to come out of this zero window thing? So there are lots of timer, not only the retransmission timeout, but other timers are also maintained in TCP implementation. So there is a persistence timer. After some time, this sender will send some dummy probes. Are you okay? Are you now okay? And getting that dummy probe, if some space is remaining, some space is vacant now, receiver can send the window size, and again the process can start. So I'm just telling you this thing or showing this slide to you that receiver has power to even install the sender if receiver feels so. So some more details if you want to explore how in RFCs things are decided or defined. So there are some variables send.una. Fine. This represents the first unacknowledged packet. First unacknowledged packet or oldest unacknowledged packet as before. Send.nxt is the next sequence number which can be sent without waiting for any acknowledgement. Send.snd.wnd is the window size from left edge to right edge, or it gives the number of unacknowledged packet. Fine. Send.wnd. Number of unacknowledged packet which can be there in flight at any given time. If you see the usable window, if you find out usable window is from 29 to 36. If you see the usable window is 29 to 36, and how to get the size of usable window which can be sent, because beyond right edge you cannot send. So it is very simple. You can use this equation send.una, which is 20 here, 20 the oldest unacknowledged packet, plus send.wnd. Send.wnd is this from left edge to right edge. Fine. Minus send.nxt, which is the next sequence number. So if you can see that the usable window is 20 plus 17 is send.wnd minus 29, you'll get 8. So 8 is the usable window. 1, 2, 3, 4, 5, 6, 7, 8. 8 packets or 8 segments can be sent more. Now suppose in this snapshot, receiver sends a ZWA, which is unlikely because receiver has previously advertised कि नहीं नहीं हम 36 तक और इतनी बड़ी विंडो का जगह है मेरे पास. But at this particular moment, which can happen due to some problem at receiver, which can happen, and this happens. Receiver suppose अपने वादे से मुकर रहा है, like it is not keeping its promise. It has advertised something and not keeping its deal. And suppose at this particular time, it sends a ZWA, zero window advertisement. So what will happen? Which also acknowledges packet number 25. Which also acknowledges packet number 25. वो एक ने ZWA भेजा जिसने पैकेट नंबर 25 भेज दिया. तो नेक्स्ट विंडो कहां से शुरू होगी? 26 से. विंडो का साइज क्या होगा? send.wnd will be 0. और नेक्स्ट सीक्वेंस नंबर हमारा क्या है? वो चेंज नहीं होगा, वो 29 ही रहेगा. तो if you see and put it in the equation, so send.una would be 26, window size will be 0, and this should be minus. This should be send.nxt. So there is some error. Let me correct it. बच्चा लोग. So this is minus 29. Minus 3. Now this is problematic. If you see RFC 793 and 1122, why I'm including this? Because I have faced this problem while doing some of my work, where we are trying to control the behavior of TCP in wireless scenario. If you see RFC 793 and 1122, you'll find that shrinking of window is discouraged. And it is stated that TCP receiver should not shrink the window. However, TCP sender should be robust against any such window shrinking. And window shrinking, what they are saying window shrinking of such kind which can result into negative usable window. Which can result into zero window, that's okay, but it should not be negative. Whatever shrinking you are doing, if it result up to 0, then no problem. But if TCP sender, if shrinking is of such a kind that your usable window is becoming negative, first of all, it is discouraged. Receiver should not do this thing. But in any case, if receiver has to do that, that sender has to be robust against this happening. And only this is written there. And actually, this unclear statement or RFC led to variations in different TCP implementation. You see in iOS, you see in uh, Mac OS, you see in Android, you see in Windows, you see in Linux, or with different versions of Linux, you'll find variations in different operating system, different implementation, and that is because of this unclear thing in the RFC. RFC has kind of opened the thing. It's an open kind of scenario where everybody has to be robust against. So now everybody is doing providing robustness in their own manner, and that's why different uh, variations are fine. Error control and retransmission timer. This is a most important topic. I'm just introducing it right now, and we'll be taking up this in detail, maybe 2 lectures on this. And please be very careful because this is required. TCP has to maintain a retransmission timer for each connection. Timer is started during a transmission, a timeout causes a retransmission. Now in wired networks, because TCP was developed for wired networks, what they have found out in various evaluations and tests and simulations, that in wired network, very seldom there is any bit error. So it is safe to assume that if there is any error, so you will not get any error most of the time. Your bit errors are not there in the wired networks until unless you cut the wire, or until unless there is a lot of noise or some crosstalk. So what TCP does, TCP couples error control and congestion control. एक्नॉलेजमेंट क्यों नहीं मिलेगा मुझे? एक्नॉलेजमेंट इसलिए नहीं मिलेगा, या तो पैकेट ही नहीं पहुंचा, या पैकेट गलत पहुंचा, या पैकेट सही पहुंचा और एक्नॉलेजमेंट नहीं पहुंचा. 3 सिनेरियो. पैकेट गलत पहुंचा इज वेरी रेयर. मोस्ट ऑफ द टाइम पैकेट रास्ते में ड्रॉप हो गया, इसलिए पैकेट वहां नहीं पहुंचा, और दैट्स व्हाई आपको एक्नॉलेजमेंट नहीं मिला. And what they have found out that 99.99% of the time you are not getting the acknowledgement in time because packet was either dropped or acknowledgement was dropped or packet was delayed, and that's why the acknowledgement was delayed. So what they have assumed that if there is a lack of acknowledgement, it is due to congestion. Now this retransmission becomes important because retransmission is not only a normal retransmission, it is going to start or trigger the congestion control also. Because now you are saying that if a acknowledgement is not reaching within a stipulated time, it is due to congestion. Now the question here is how to set the retransmission timeout. Nitin, 5 minutes, huh? How to set the retransmission timeout value. Now, if the timeout value is too small, it may result in unnecessary retransmissions. If the timeout value is too large, it will be long waiting time before a retransmission can be issued. बेकार वेट करते रहोगे और जल्दी से retransmit करना चाहिए था. The problem is that delays and traffic condition of network is not fixed. They are variable. So your retransmission timeout value also has to be adaptive. It should adapt to the current network condition. And that's what is important here. We'll discuss more on it later. So we'll stop here. We'll start from here only in the next lecture, and we'll discuss congestion control and acknowledgement dynamics in more detail. If there are any question you can ask, otherwise you can leave. Okay, if there are no question, then you can leave. Most have already left.